All right, thank you to the organizers for giving me this chance to try to summarize rather briefly a very interesting field. I don't have a lot of time for this, so I'm going to try to focus on two particular experiments, and my apologies in advance to those that I may miss in this. I also want to try to emphasize the connections between the field of ultra-high energy cosmic rays and high energy physics. So ultra-high energy cosmic rays is the study of what is often called the end of the cosmic ray spectrum, which means for our purposes cosmic rays at energies of 10 to the 18 eV, 10 to the 19, 10 to the 20, and above, and that's a lot of energy. So immediately you can see it's appropriate to have it at a high energy physics conference. The techniques are being used now by the two projects I'm speaking of are venerable techniques, ancient ones, if you will. The flux of these cosmic rays is so incredibly low that they cannot be directly detected with anything of reasonable size. So what you detect are cosmic ray air showers. You use the Earth's atmosphere as a target. And there's two ways then to detect these air showers at the ground. One is with an array of surface detectors. And whoops, yikes, getting way ahead of myself there. With an array of surface detectors which detect the air showers when they hit the ground. The other is the air fluorescence technique, which can actually track the shower across the sky as it excites atmospheric nitrogen. Bottom line on the two techniques is that the surface arrays are good for statistics because they sample 24 hours a day all the time. The fluorescence detectors are particularly good at getting the energy of the air shower. They work very much like a high-energy physics calorimeter. The two projects I'm going to talk about are the two that are working very well right now. The first is the telescope array, which is located in sort of the central part of Utah in the USA. This is a map of the surface detectors on the ground. They cover an area of about 700 square kilometers, 500 stations, plastic scintillators. Each station is 3 square meters, and they're separated by 1.2 kilometers. On the edges, well, this optical device is not so great, but you can see 3 fluorescence telescopes which look out over the array, okay? And fluorescence telescopes operate roughly 10% of real time. They're so sensitive they need dark, moonless nights. But events that are covered by both surface and fluorescence detectors are particularly valuable. This was described in much more detail by Charlie Ray at this meeting, and I urge you to go there for details. The other experiment is the one that I'm particularly involved in, and that's the Oj Observatory. It's larger than the telescope array. The idea is similar, though. It's got a very large surface array covering 3,000 square kilometers and with 1,600 surface detectors. In this case, they're large tanks of water, each 10 square meters. They're 1.5 kilometers apart from each other. In this case, there's 4 telescopes, fluorescence telescopes, looking out over the array. And this was just a nice picture. You can see I've labeled some other things, but I won't spend a lot of time talking about them. Some of those labels are with radio detectors and things like that. This is located in the southern hemisphere in western Argentina. And so we see pretty much different parts of the sky from the telescope array and Oj. Not completely, but for the most part. I'll open up then with with one of the more interesting results that's just coming out now from the telescope array. It's a simple enough idea. You look on the sky and ask, where are the cosmic rays coming from? I suppose I should have said, what's the point of all this? At the highest energies, it's a simple question. We don't know where they're coming from, the cosmic rays. We don't know how they get accelerated to such preposterously high energies, well beyond the LHC, well beyond anything that will ever happen on Earth, probably. So step one, look, see where they're coming from. This is Charlie presented this. This is a recent result. I think it's pretty neat. The telescope array has collected over 1 million events over the last 5 years. If you look at the highest energy events, okay, that are not completely horizontal coming in on you, and you smear them around a little bit by 20 degrees and look at the sky, what they see is a hot spot, okay? On the top, on the top you see a map of this. This is in the northern skies. On the bottom, you see the significance of it, and this is somewhere between 3 and 4 sigma against an isotropic background. So that's pretty interesting. Now, I'll caution you, as Charlie did in his talk, that assessing the trials factor, if you will, is a little tricky. So the paper describes things pretty well, so I would send you there. In any case, this is interesting, okay? And this is very new. Now, Oj had seen something kind of similar to it with some distinctions. We published this a few years ago, just again looking at the sky. And we looked at the hottest spots in the southern sky. And we found one sort of near Centaurus A. Centaurus A is an active galactic nuclei and jet structure that's the closest to Earth, so it's kind of an inviting target. And this was what we saw. We saw events not directly from Cen A, but within about 20 degrees, okay, and spread out. So it's not exactly the same kind of thing that we're talking about, and yet the size scale of this, to me, is intriguing, okay? Now remember, what must happen to charge cosmic rays is they're going to be deflected on their way to the Earth from wherever they came from, okay? And in both cases, both experiments kind of see blobs kind of smeared out in about the same size scale. Without better knowledge of the galactic magnetic field, I'm not sure where to go with this except to collect more data. So this is exciting, and I'm particularly intrigued by the new telescope array result. Now, let me give you a little background. I think most people are familiar with this. Other than just looking at the sky, what can you learn? A little background on this is just to look at the energy spectrum of cosmic rays when they arrive here, okay? And to interpret that, the first thing you need to know about is something called the GZK cutoff, Greisen-Zatsepin-Kuzmin, which was invented by those gentlemen soon after the cosmic microwave background radiation was discovered in the early 60s. It's a simple notion to a particle physicist. Cosmic ray protons interacting with very low energy cosmic microwave photons will get above the threshold for the first particle interaction, the first inelastic interaction, which is photoproduction, the delta, or similar. A cosmic ray proton above a few times 10 to the 19th starts to do this. What happens is the delta decays rapidly and a proton emerges with less energy, okay? So, and this can happen over and over again. Maybe a neutron comes out. It doesn't matter very much. But over long distances, if it happens repeatedly, what it means is you will never see a particle above a few times 10 to the 19 eV. If you do, it must have come from relatively nearby in the universe. And by that I mean about 100 megaparsecs. So that's why in the last two plots I showed you from TA and from Oj, that there was a cut made on the highest energy events. Those are the ones that you think you might have a shot of seeing them point back to where they came from. So that's a key thing. Nuclei, if the primary cosmic rays were nuclei, they would photodisintegrate through the giant dipole resonance. It happens that the thresholds and distances are similar. Interaction lengths are quite similar for that. Nuclei really take it on the chin, though, because if they get broken up, you don't see them again. They're gone. Okay? So heavier nuclei, if they undergo this, you won't see them. You'll see lighter nuclei coming in. And they have an even shorter disintegration length because they're easier to break up. Okay, so if you have a collection of sources and you're looking at the cosmic ray energy spectrum, what will you see? You should see it suppressed. If the sources are anything other than close by, you should see the spectrum fall off at about this energy. So here's the results, the relatively recent results from the telescope array and from Oj. Both are showing similar features, okay? At the highest energies, you see this fall off, which is quite consistent with that GZK suppression, but I'll give you another option for that in a second. Both experiments see that. Look at the dark spots here, the dark points. Those are the highest statistics on that plot. Both also see a little dip and a change in the spectrum. This is the flux times e to the cubed for the purpose of just flattening it out so you can see structures in it. And both experiments are really showing the same thing that way. Now, let me talk about interpreting that briefly. Here is what I just described. If you had a power law, whoops. How many speakers have said whoops here? You start off with a power law spectrum. Here's what this is what the GZK effect would look like. You would see it getting suppressed above a few times 10 to the 19. This is a cartoon. Don't press me on the details of this too closely. Where did they go? If it were protons, as I said, they kind of end up at higher energies, so or at lower energies. So all the ones you lost would start to pile up. You might see some stuff in there. If you're really lucky, I think this is doubtful, you might actually see it recover. Remember, we're looking at a cross-section process here. I think that's really unlikely, though. The fluxes would be really too low. Okay, so this is what a proton flux would look like. But here you are. Here you see this. You see a cutoff like this. Could there be another explanation? Yes, there could be. Could it simply be the source accelerator running out of steam, running out of power? If that was the case, all right, then different primaries would have a different cutoff, okay? And the basis for this is really simple-minded. It's that if this is an electromagnetic process doing the accelerating, well, I'd expect if protons have an Emax, then iron would be 26 times Emax, all right? So this is a real question. I've shown you that both experiments do see a suppression, all right? And the question is, are we seeing the GZK cutoff, the sources being throughout the universe and telling us that? Or are we seeing some effect from the source, the accelerator itself? Now, this is a very busy plot. Oh, I'm sorry, but I've plotted here both the telescope array and Oj points together, all right? The blue points are the telescope array spectrum, and the black points are the Oj spectrum. And there's a lot of things to talk about here. I'll bring this back a little bit later. First off, I want to show how very, very similar, close the measurements are, okay? Below roughly 10 to the 19 eV. They're really on top of each other. There's a lot of lines here which can kind of fool the eye, which is why we put them on, I suppose. But if you just look at the points, there's really excellent agreement down here. And then there's a deviation between the two experiments, okay? Now, we're not positive we understand the origin of that, okay? Up here, notice that error bar. That is the systematic uncertainty in a point for Oj. There's a 14% systematic uncertainty. And I'm multiplying the flux times E, so that gets tilted a little bit. My point is that even up here, the two experiments agree within the error bars, okay? But it's still intriguing. It makes one speculate with little basis that maybe the northern skies are different than the southern skies with the spectrum. I don't know. Time will tell. The other thing is the lines that are drawn through it, okay? Arbitrarily, we have fitted a spectral shape for the TA data based on a GZK suppression. And for Oj, instead, we fitted in a bunch of intermediate elements cutting off at progressively higher energies, like a source exhaustion, okay? My only point here is that either explanation seems workable just by looking at the spectral shape. Okay, so you want to get after the composition of the cosmic rays. That's something you do. You would look and say, well, to tell it apart, let me see if I've got heavier nuclei in there. The only way to really do that effectively now is to look at the depth of shower maximum. Okay, showers start in the atmosphere, then they reach a maximum. That depth of maximum is closely related to the interaction length of the primary. How deep did the primary come in? Iron nuclei would go 4 times less deep than protons would because their interaction cross-section's that much bigger, okay? So anyway, this has been published several times, and again, the lines on the plot, you can see there's different interpretations. The telescope array seems to be running along and suggesting that the composition is not really changing. It's very proton-like, whereas Oj is really suggesting to you that something's happening, and there's some heavier elements getting mixed in. This is a difficult question. I will only offer an opinion that, in my view, the data points differ from each other far less than the interpretation of the data points based on the models. It's difficult to just overlay these two plots, and I'll get to that later. Okay, so let me get going here toward the end and discuss specifically high-energy physics and cosmic ray connections. What can we learn that's of use to high-energy physics and vice versa? So there's an air shower. Can you see the Higgs boson in there? Me either, so we're not going to talk about that. Instead, here's one of the things I was just discussing. This is the distribution of the depth of maximum of showers measured by Oj. Just a histogram. Most of our showers in this energy range of showers, most of them reach maximum about 700 grams in. Vertical atmosphere is about 1,000, okay? And then there's this long tail. Well, this long tail is telling you is an exponential distribution, and it's closely related to the interaction lengths of the primaries. You fit that. And it's a nice exponential out here at the high end. This is something we'd recently published. And there's the slope. This technique was really invented over 30 years ago by the fly's eye people, by the way, the precursors to the originators of the fluorescence technique, and to which telescope array and Oj owe a lot. Anyway, from this you can simply derive the interaction length. It's a little bit less than the number here because of some systematic things, but also, if there are other nuclei in here, remember, you're up at the high end. So if you've got protons, they're dominating out there, all right? So here's the bottom line from this, is that with the interaction length, we can measure the cross-section. And so we did. There's the proton. We measured the proton air cross-section and then bring in a little Glauber, and this is what you get. I just wanted to emphasize how far above the LHC levels this is, which makes it useful to us. and there's the numbers. So that's a good thing. From that, Marty Block and Francis Halsen delivered some papers recently where they really ran with it, with that result, among others, okay? So I'm just waving this around to show that there is value in looking carefully at cosmic ray results, all right? That the proton is becoming its black disk self, and we're approaching an interesting regime, all right? We may never get there, but they quantify how close we're getting to it. Another thing, too, is that the interpretations, if you were paying attention, the different curves I was showing you are based on, for us, 3 different interaction models. These are used, the development and the work on these is standard in the cosmic ray business. It's also widely used at CERN. The same people are on both CERN experiments and on our experiments at Oj. All right, so this is a good common area where we're learning a lot from each other. The results are good, but they're not perfect. There is no one model that does it all very well for us. For example, Oj sees too many muons compared to any of these models. All right, not enormously, but it's not right. There's something still not right about the modeling. This is just a plot I took from a friend who presented it at the European Cosmic Ray Symposium a couple of years ago, the EPOS model, and how much detail is needed in it and how closely connected it is to the CERN efforts to get this right. So what's next? Well, we're still in search of the sources. We're still trying to understand the nature of those bumps and changes in the energy spectrum, and we're still trying to understand the details of the hadronic interactions, as I was just suggesting to you. How do you do this? By trying to study the composition, again, trying to find better ways to smoke out whether there's protons or nuclei in there, and frankly, just statistics will help you a lot too, getting a lot more events. Get bigger, okay? At this moment, both telescope array and Oj have a number of enhancements underway, running, in addition to the basic surface detector and fluorescence detector. There's radar measurements being made. There's radio measurements, megahertz, and other such things. There's regions of the experiments that have tighter spacing on the surface detectors to push down to a little bit lower energy thresholds. Another thing at TA is the low energy extension, which is really going to push down in energy down to a regime where other air shower experiments have taken a lot of data and connect up with them. The future, and these are the big projects, is the telescope array is aiming to expand its overall size quite a bit, up to 3,000 square kilometers. And Oj is aiming to expand the muon coverage, to put muon detectors on every surface station in order to do a better job of doing the composition. One of the big differences between a nuclear shower and a proton shower is nuclear showers have a lot more muons hitting the ground, okay? And that's what we're looking at here. To get down to lower energies, you see this business, this dashed line here is presumably cosmic rays coming from our own galaxy and tailing off and dying, and then the extragalactic components coming in. That's why you want to look at the lower energy. You want to see this transition region carefully, and you'd like to know the composition up here. Okay, so that's what's driving this next generation. So my last slide. We're competitors, but we're working very, very closely with each other. In particular, there's been a couple of meetings on ultra-high energy cosmic rays. The last one was in December of 2012, all right, at CERN. Brought together a number of CERN community and theorists, as well as the cosmic ray people. And we formed some permanent working groups between the two experiments to try to understand this. It's very interesting. It's interesting particle physics, if nothing else. And for that reason, I heartily invite all of you here to come to Zions Park in Utah in October of this year for the next meeting. Thank you very much.
Thank you for the very clear presentation. This presentation is open for question and comments.
A few years ago, as you, I think, reminded us, Oj presented some evidence of clustering of the highest energy cosmic rays from certain possible astrophysical sources. Then a little later, I don't remember whether it was statistics or what, the evidence became somewhat weaker. Now tell me please, if I understand correctly, the statement at the beginning of your talk. If I smudge up the points from which certain high energy, very high energy cosmic rays come from, taking into account the possible smudging of direction due to the intergalactic magnetic fields, the enhancement from a certain broad region reappears. Is that a fair assessment of what you told us with it, that big red blob top right in your plot?
Well, you asked a lot, you raised a lot of questions there. Let me pick the ones I'll answer.
No, it's only one.
This is a blob. Okay, now remember, whoops, there he goes again. These data, the telescope array, they've smeared out the data in order to try to accommodate the fact that it's with a finite and not a huge number of points, it's hard to see things. And clearly, that blob is resulting from the fact that you have a number of points which are unusually close to each other, at least in this sense, okay? Now, the 20 degrees could be indicating the deflection of magnetic deflection. You try to correlate things a bit with energy that way. If it was a nearby source, then it would be the galactic magnetic field. That's one thing. At Oj, as I was saying, we would have a similar kind of picture in the southern hemisphere, but it would also have been offset from Cen. I have nothing to say about Cen except it was close, so that's why we looked at it. Okay? But the smearing is primarily, it's been done intentionally here, but the physical smearing is probably the result of galactic magnetic fields pushing things around. The angular resolution itself of both experiments is pretty good. It's about a degree or less at these energies, and these are the highest energies. If I can comment on what you started your question with about a few years ago, Oj, yeah, we saw when we looked at the arrival directions and asked, do they correlate with nearby matter, okay? In particular, we compared to a catalog of AGN, and we collected only those AGN that were close, relatively close, okay? And there's not a million of them like that. And we found, yeah, within a few degrees, there was an unusual correlation. And at the time, it was, when we saw the analysis and decided to write the paper, it was about 4 sigma. When the paper got published, it was around 3 sigma. Today, it's around 2 sigma. So I saw no reason to put it in a highlight talk, of all things. I will mention, though, that the telescope array has done the corresponding analysis, and they, too, see something in the vicinity, 2, 3 sigma excess. I'll leave that to Charlie. But the two experiments, neither sees a particularly significant effect, but they see the same amount of insignificant effect. So we can't sell that, but we'll just keep looking at it, okay? That's the best I can say.
But that would largely get rid of the effect that you call trial factor and particle physicists call look elsewhere effect. So that's encouraging.
Okay, let's just have one more question back there.
I noticed that there was no, you didn't have Agassiz points in the plots that you showed. Agassiz, the points by Agassiz. you don't ever show them. I'm just wondering, are they considered to be wrong, or?
Well, this is the first talk you've ever seen me give, so you can't say I never show them, but I...
But you're not the only one who does that.
The Agassiz points are fairly old. The results from other experiments do not support the Agassiz points. They had fair error bars on them and systematics. I mean, I'm hesitating to say they were wrong, but I'm just, those points are 20 years old now, and all the more recent experiments don't support that particular observation. I think that's the best way I could put it.
Okay, I think that concludes well. Let's thank the speaker one more time.